For question 1, we have intrinsic carrier concentration equal to 2.4 multiplied by 10 raised to the power 13 per centimeter cube, and doping concentration is provided 4 into 10 raised to the power 13 per centimeter cube. We have the formula for free electron concentration, which is clearly the values of intrinsic carrier concentration and doping concentration are comparable. Therefore, we cannot ignore intrinsic carrier concentration. After calculating, the free electron concentration comes out to be around 5.124 into 10 raised to the power 13 per centimeter cube. From mass action law, we can find the whole concentration also. After calculating, the whole concentration will come out to be around 1.124 into 10 raised to the power 13 per centimeter cube. Question 2 is one of a kind question. It is not a difficult question, but still you have to think very hard to solve this question. You know that conductivity is equal to. Now, when you see the word maximum resistivity, one concept that should instantly knock your head is the concept of maxima and minima, which you all have studied in mathematics. For maxima and minima, there should be a function, and for easy calculation, the function should be defined in one variable only. Now, charge is a constant, mobility is also a constant because temperature is kept constant. So, the only variables we have is free electron and hole concentration. Also, by mass action law, we can write hole concentration is equal to square of intrinsic carrier concentration divided by free electron concentration. If we put this value in conductivity, we will find now, for finding the extreme values of conductivity, we have to find the differentiation of conductivity with respect to free electron concentration and have to find all the values where the differentiation becomes 0. Negative sign makes no sense at all, since concentration cannot be negative. Therefore, we have the extrema at free electron concentration equal to intrinsic carrier concentration multiplied by under root of mobility of hole divided by mobility of free electron. Now, this is also a very important point that even though it is an extrema, then again, which type of extrema is this? Is this a maxima or is it a minima? To find that, we have to double differentiate the function with respect to the variable and have to find the value of the resulting expression with the extrema values. If the value is positive, then it will be a minima, and if the value is negative, then it would be a maxima. Here, the double differentiation of conductivity with respect to free electron concentration will give us this expression. Now, after putting the value of the extrema of the function, you will find that the value of the double differentiation is actually positive. Therefore, this value of free electron concentration is the point where conductivity of the semiconductor will be minimum. It means that for minimum conductivity, free electron concentration will be equal to, and by using the mass action law, you can find the value of hole concentration to be equal to intrinsic air concentration multiplied by under root of mobility of free electron divided by mobility of hole. So these are the values of hole and free electron concentration at which we will find the minimum conductivity. So the minimum conductivity will be you also know that resistivity is equal to 1 upon conductivity. Therefore, for the maximum value of resistivity, we should have the minimum value of conductivity. And we already have the formula for minimum conductivity. Therefore, maximum resistivity will be equal to now you simply have to put the values. After calculating the expression, we will find maximum resistivity to be approximately equal to 49.78 ohm centimeter, and in kilo ohm centimeter unit it will be 0.049 kilo ohm centimeter. For the third question, we have to find the potential difference across the end of a semiconductor, and we know that the potential difference equal to resistance multiplied by current. Also, we know that resistance is equal to resistivity multiplied by length of the semiconductor divided by area of the semiconductor. And the third equation that we know is resistivity is equal to 1 upon conductivity. From these three equations, we can write potential difference is equal to and conductivity for p-type semiconductor is equal to magnitude of charge on a charge carrier multiplied by mobility of hole multiplied by concentration of hole. This will give potential difference equal to now we have to simply put the value of different parameters. After calculating the expression, potential difference will come out 31.5 millivolt, or in other words 0.0315 volt. For the fourth question, resistivity of a n-type silicon sample is equal to, and also we can assume that n is approximately equal to doping concentration, which is the general case. For doping concentration, we have now we have to simply put the values. After calculating, we will find the doping concentration to be equal to 10 raised to the power 16 per centimeter cube. For question 5th, we can assume that the semiconductor is in equilibrium. Therefore, net current will be 0, and net current is equal to diffusion current plus drift current. For holes, diffusion current is equal to and drift current is equal to by Einstein relation. We can write diffusion constant of hole divided by mobility of hole to be equal to thermal voltage, and this expression can be modified to, therefore we will have the electric field equal to, we are supposed to find only the magnitude, so we are not concerned about the sign of the electric field. Now we simply have to put the value of different parameters. After calculating, the answer will come out to be around 1198.6 volt per centimeter, which is equal to 1.198 kilovolt per centimeter. We have put the value of thermal voltage to be equal to 0.026, as the value of thermal voltage at room temperature is 26 millivolt. Here in the question it was not provided at what temperature we have to consider this question. So we have assumed that the question is asked at room temperature. However, it should be provided in the question itself, but that's how it came in the gate. Magnitude of electric field is equal to potential difference divided by distance, which will give the magnitude of electric field to be equal to 10 volt per centimeter. We know that the velocity of electron is equal to mobility multiplied by electric field, which is equal to now the time taken by the electrons to move from one end of the bar to the other end is equal to length of the semiconductor divided by velocity of electrons. Length of the semiconductor is provided 1 centimeter, and we just found the velocity to be equal to 10 raised to the power 4 centimeter per second. We will have time equal to 10 raised to the power minus 4 second, but since the answer is asked in microsecond, we have time equal to 100 microseconds, and this is the final answer.